And but in the code, how are you going to set fs? What's the mechanism for setting the sample frequency? Timer period, right, same. Yeah, I got from both, I got it in stereo. Yeah, it'd be the timer period. So the timer period, you're going to set a timer to time out after n cycles. And that is going to throw a hardware event which triggers an interrupt service routine. So you can think of the interrupt service routine as executing at the sample rate. So if you put all of the sampling code in the interrupt service routine, then you're guaranteed, as long as the interrupt service routine is not too long. What do I mean by too long? If the interrupt service routine takes more than delta t to execute, you're in deep kimchi. It won't work. Right? Because it'll take longer to execute than the time between samples. So again, with that background, are there any questions about direct digital synthesis? Don't be shy. Yes?
Can you repeat what you said about what goes in the ISR?
Say again?
Can you repeat what you said about what goes in the ISR?
So what is going to go in the ISR is everything related to one sample of the sound. So in the ISR, you're going to need to update sign 1, sign 2, and voice. So to expand that a little bit more, what's going to be in the ISR, and this is a timer ISR, and it's ticking, the timer is timing out at a rate of 1 over fs, right? So what do we need to do in the timer ISR? Well, we certainly need to increment some phase accumulator, and let's call it accumulator 1. We need to increment phase accumulator 2 because we need 2 sine waves at different frequencies. We need to derive a speech sample. How many people are going to use spectral synthesis, and how many are going to use wave synthesis? Hold up your hand for spectral synthesis. Oh, okay. How many for wave? So you're voting with your feet, which is a good idea because the wave system is at least a factor of 10 easier. That doesn't necessarily sound better, but it's much, much easier. Okay, so in that case, we're just going to say we're going to decode the wave information for voice. In other words, we're going to choose a 4-bit sample from the 8-bit packed binary we'll talk about in a minute. Or you're going to come up with your own scheme for storing. You can store voice in lots of different ways. You could do 2-bit adaptive differential pulse code. But some way or another, you have to decode a wave file voice sample into for output, unless you're actually going to do speech synthesis rather than just playback. You laugh like you're going to do that. Yes, it's possible.
We took your allophone suggestion.
Yeah,
Oh my God. Okay, so you used, did you look at the allophone table?
yeah, we
Yeah.
mostly
It says
we've
all-
mostly done it.
MATLAB says the digits.
Yeah, though we used your header, we used your script to make the header file.
So there's one of the old speech synthesis pages from the dark old days when I used AVR has a table for an allophone synthesizer. An allophone is part of a word, like O or E or T or T. Right? So it's about 60 sounds that make up most of English. And you can take pieces of that allophone table and put them together to make words. So you're concatenating these things, and it sounds really robotic, would you say? Discontinuous, clunky, but understandable. So that's another possibility. At this point then, the next thing you have to do, you must do, is assert the chip select for the DAC. So you're going to assert the chip select for the DAC, and then you're going to write to the SPI channel, DAC A control data, and you're going to add sign 1 and sign 2. Then you're going to wait. You must wait until this is done, and then deassert. Is deassert a word? Unassert? Turn off? I don't know. Deassert chip select. And then immediately again, assert chip select. Say, uh-oh, I'm going to deassert it and then reassert it on the next instruction. And what should immediately come to your mind is, how long does chip select have to be high for it to be valid for the chip? And the only way to find that out is to dig down into the data sheet of the DAC. And you flip through that for a while, and you kick a hole in the wall, and you dig some more, and you find that there's a value called TCSH, which is the chip select hold time, which is 15 nanoseconds. So, can I do it on the next cycle? Yes or no? What's the cycle time of the CPU? What's the cycle time of the CPU at 40 megahertz? 25 nanoseconds, right? So the answer is yes. You can do it on the next cycle. Then we're going to write to the SPI with DAC B control plus voice. Wait till it's done. Deassert chip select and exit. The nice thing about putting all of the interactions with the DAC in one interrupt service routine is that you can guarantee that there will be no collisions. Let's say that you you figured out that you can sample the voice at 8, but you need to have for distortion, to make the distortion for like homework problem 1, you have to sample at 10 kilohertz. They said, well, I could write an interrupt service routine that runs at 10 kilohertz and updates channel A, and another one that runs at 8 kilohertz and updates channel B, and that won't work because you can't because you can only do one transaction at a time. And if 2 interrupts are running, what happens when they collide? Or maybe you want to find out. Yes?
Can you have like the slow one write to the SPI and the fast one only updates the value?
You definitely could do that, but then you're updating at the slow rate, of course, not at the fast rate.
But you can possibly just achieve different frequencies.
So the safe way of getting different frequencies from one interrupt service routine is to just check if, let's say you're sampling one at 8 and one at 16, is to do every other one in the same interrupt service routine. You take the 8 and 16 kilohertz voice samples, you run the interrupt service routine at 16 kilohertz, you take the 16 kilohertz voice samples, you output one on every interrupt, and if you're running the synthesizer at 8 kilohertz, only output a value on every other interrupt. Done. One interrupt, much safer. Also, interrupts have a fair amount of overhead. I think it's probably going to take longer to get into the interrupt than it's going to take to do everything else in this interrupt except the wait. How long is the wait going to take? 16 cycles. At the SPI frequency, whatever that is. So in my code I set it to 20 megahertz, which is the practical maximum for this chip. I would actually drop it to 15 megahertz. So it's going to take around a microsecond at 15 megahertz to do 16 bits. Any questions on that?
Question on something else.
All right, push my stack. See if I care.
So, a few lectures ago you mentioned that 2 to the 13 is the bare minimum sampling rate you can...
8192, yeah.
Can you explain how you got that number?
No, because I hypothesized it. I said, let's say that, let's pretend this is the lowest possible frequency.
Oh, so it's not actually that.
It is actually lower than the lowest possible frequency. Let's go back and look at homework 2 again. 8 samples per cycle, 8192 hertz, right? That's what the sine wave looks like. If you're putting out a 1 kilohertz sine wave at 8 kilohertz, that's what it's going to look like. It's going to look ugly. I mean, you have to squint a little bit. All you're going to really see are these samples, right? You're not going to see the jagginess in between. Although that's how the DAC is going to interpolate it, because it's a zero order hold DAC, right? So it's going to interpolate it as a square wave. So the spectrum that sine wave represents, that sample sine wave represents when analyzed at a higher frequency, looks like this, right? There's the fundamental. This is the first error term corresponding to the sample frequency. Is it good enough? What the spec says is that the first error term has to be 20 dBs below the fundamental. Is it? Almost. Close. Close, what does it say? Close only counts in horseshoes and hydrogen bombs. So it's not good enough. That means that 8192 is unlikely to be good enough. My argument that below those many lectures ago actually just gets worse if you turn the frequency up. You have to, well, no, I mean, so you have to turn the frequency up to get enough samples to represent a, let me not say that way. You have to sample often enough so that you have a good enough approximation of the sine wave that the spectrum allows you to get 10-to-1 signal-to-noise ratio. Let me remind you that questions 1 and 2 interact. If you sample fast enough, you may not need a filter at all. If you filter enough, you may not need a fast sampling rate. So your answer for 2 depends upon your answer for 1. I sometimes hesitate to say that. Sometimes it's better to say nothing than to say too much. Any other questions? Pop my stack. Pop stack back up to interrupt service routine.
You talked about doing this without the CPU involved at all. Can you talk about that again?
Yes. Sean, would you like to talk about that? Yeah. Hold on. So it is possible to drive an SPI channel using the direct memory access device. There is a mode called a framed transfer on the SPI that allows you to use a direct memory access channel to spit out data to an SPI endpoint. So it's called framed SPI. And as far as I can tell, it is included on the chip specifically so that DMA can output to the SPI. Once you set up a DMA channel, I haven't talked about DMA yet, that's sort of next lab, but the background is that the memory system on this chip is not actually a bus, it's a crossbar switch. And so you can have several memory conversations going on at the same time, as long as the start point and the end point are not in common. You just use different points on the crossbar. So for instance, the CPU can access flash. The CPU is a bus master, flash is a bus slave, is a crossbar slave. So the CPU can get to flash at the same time that the direct memory access bus controller, it is also a bus master, can talk to the peripherals, which is a different bus destination, a different endpoint on the switch. So you can have the two conversations going at the same time. The CPU can run at full speed, the DMA can barf out stuff at full speed, and they do not slow each other down. You've just doubled your bandwidth. For some things that can be very good. For this, it's not so necessary. In fact, it's not necessary, although it's kind of entertaining. If you were simultaneously generating a 500 kilohertz sample rate for the DMA and generating a 4 megabit per second bit train for updating a television and recording from the analog to digital converter at 500 kilosamples a second, you would have to use DMA or you would run out of cycles. There's not enough time, not enough interrupt service routine time to do those 3 operations at once. But with DMA, they use 8% of the CPU. We'll talk about DMA later. That's just a quick introduction. It is another bus master. It has very limited arithmetic capability. It can calculate a cyclic redundancy code, and it can move data from memory to memory, and that's about it. Do you have a question?
Yeah, not about the DMA.
Sure.
More about the DDS. So, in your DSP code, you use the formula you gave us last lecture, the F out equals Fs over 232 times the increment.
Mm-hmm.
It's just a reverse in the code there. And so I played around with it and hooked this to the scope, and I saw the FFT in the waveform.
Uh-huh.
And we get something like this, but the oscilloscope doesn't measure the output frequency that we set in the code. So, like, I think by default, the DSP code had like 100 hertz, and the scope showed like 140. And then when we tried playing around with it, it just didn't agree at all.
So you mean the position of this peak, when you did FFT, or are you talking about in the
Well,
you're talking about the time-based measurements of the frequency on the scope?
yeah, the FFT looked fine.
Wait a minute. If the FFT looked fine, the input signal's got to be fine.
The input signal also looks fine in terms of it's sinusoidal, but it doesn't read it at like 1500 hertz, for example.
Was this at 1500 hertz? You say looks fine. Was it at the right frequency in the FFT?
No. Okay, so what I mean by looks fine is that the harmonics.
Okay, I mean, the general structure looks right.
Yeah, the
Okay.
structure is right, but the frequency reading is.
Well, I can't answer that by guessing, but I'll be happy to look at your code. There's probably an off by pi or something in there. But this does work
Okay.
as long as you are calculating the sample frequency correctly.
Okay, and then one follow-up question. In that code, by default, you set the sample frequency to a value, and then today you're saying use the timer cycle time. So,
Huh? I was using timer cycle time in all of that. FS is always set by a timer in my code because I'm always doing an interrupt service routine based.
okay,
Right. The increment is set in the code,
right.
but FS is set in everything I've written is set as the execution rate of an interrupt service routine. Which code are you referring to, though? Let me see if I can get it up here. Yeah, I know.
It was
There's
like
some.
the first example on the DSP.
Okay, let's go look at the DSP page. DSP. So the speech playback thing, oh, this is old. Wait a minute, let me refresh this. Yeah, transfer function measurement. You're not talking about transfer function measurement, or are you? Or are you talking about the speech stuff?
No, I'll just show you after class.
It's on that, like, test group.
The Lab 2 test code?
No, it's not the test code.
It's not. But in that, FS was defined as a local variable, 150.
I defined it as a global variable so I wouldn't have to keep writing to 100,000. But that didn't set the frequency, that just names it. I know what you're talking about now. That merely names the frequency.
So you're saying you set it based off the timer?
I set it based off the timer. I named it so I wouldn't have to keep using the number 100,000.
So where can I view how you set it?
Oh, okay. Digital signal processing, let's go look at some code, this one. So this is generating a sine wave. but the only thing that matters is where we set up the clock. So there's a timer interrupt right here. So we're opening the timer, we're configuring the interrupt for the timer, and you'll notice that the period of the timer is 150 cycles. That sets the sample rate. This happens to be set to 200 kilohertz right now, I believe.
Shouldn't it be like 150 plus 1?
It actually should be 150 minus 1. Yes. So the timer timeout controls the interrupt, which is then going to be your sample rate. So the timer period is what sets the sample rate. So what else? What other questions do we have? Fast as hell?
Yeah.
Yes. It takes a lot of the CPU.
But there's no other, like, other thing.
So let's say you want to run it how fast? 100 kilohertz?
Sure. I guess also, how do you like correspond that with, because you can only run the SPI at 15 to 20 kilohertz. So it's like,
You're running the SPI at 20 megahertz.
okay.
It takes 1 microsecond to do the transaction. Therefore, you could do 10 samples in 100 kilohertz. It's fine. That works. So the SPI transaction is fast enough for a 100 kilohertz sample rate. You could do that. The DAC will support it. The voice is going to be a factor of 12.5 slower, because it is all sampled at either it's either 12.5 or 6.25 slower, because it's all sampled at either 8 kilohertz or 16 kilohertz. Now you could go back to the MATLAB code. You could resample at whatever frequency you like. But but you can only store, let's see, flash is 128 kilobytes. Is that right? On this chip? I think that's why it's called a F128. So I think it's 128 kilobytes. So at 100 kilobytes a second, you can store 1.2 seconds of speech if you don't store anything else. That's why you don't want to go fast for speech. You want to go minimum speed for speech to save flash memory, because you're doing brute copy of a waveform out of memory. Bandwidth of speech is only about 3 kilohertz. There's a few very high-pitched sounds that help discriminate speaker and help discriminate particularly consonants. Almost all of the energy for vowels, o, e, a, e, is in 3 frequency bands, and the highest frequency band is around 1.8 or 2 kilohertz or so. Most of the high frequency energy is in the consonants. S, ha, p. Those are all high frequency sounds, right? They're broadband. The explosive sounds are broadband because they have a short time. And if you limit the bandwidth, you will have trouble, for instance, discriminating a P and a B. Because the high frequencies that discriminate P and P are gone. But you can limit the bandwidth of speech to probably 2500 hertz, and it's perfectly understandable. You can even tell who it is for the most part. What else? Any other questions? So, talking about the speech playback stuff now, that being the last topic, I started reading up on speech vocoder. So, the word is vocoder. I saw one of the first speech vocoders that was publicly displayed at the 1964 World's Fair in New York. And we were amazed to see the operator sit in the booth and talk at one frequency and have voice come out an octave higher or an octave lower. It was doing real-time recoding of frequencies. At the time, this device was, call it 6 feet by 20 inches by 20 inches. So this big. Right? Vacuum tubes, folks. And so now vocoders are used in all your cell phones to break down speech. And the basic idea is that you're going to, if we look at log frequency versus log amplitude, we're going to define a series of bandpass filters that overlap quite a lot, but are distributed linearly on a log scale, so that between about 300 hertz and about 3400 hertz, you have a dozen or two bandpass filters. And what you want to do is you want to record the energy in each bandpass filter at a rate which captures voice dynamics but doesn't require resolution at the highest sine wave frequency resolution. So the bandwidth of your voice is 3400 hertz or so, but the bandwidth of the muscles in your throat is more like 50 hertz. About the fastest you can move your lips and tongue and throat muscles is, well, somewhat slower than 50 hertz. And so in some ways, why store all the fast information if all of the interesting dynamics are so much slower? So what you do is you take the output of each of these filters and take the average amplitude averaged over some time period, let's say 16 milliseconds or so. That's comparable to the fundamental frequency of one voice cycle. It's actually a little bit short, but that's okay. But it's comparable to the fundamental of time period of your voice. So it's a reasonable time over which to average. And then every 16 milliseconds, we'll send all of the amplitudes out as the voice data. So if we had 16 filters, and we set one every the amplitude every 16 milliseconds, that would average down to one sample per millisecond. If you send raw voice, you need 8 samples per millisecond, 8 kilohertz. Therefore, you've just done an 8-to-1 compression. By sending the coefficients at a lower rate, you've compressed the speech 8 to 1. So you can store 8 times as much speech, or you can use 8 times less bandwidth, or however you want to put it. The speech vocoders on your phones use a variant on this which is more optimal. I used 15 or 16 or 18 fixed filters. The vocoder on your phone says, for the speech that this person is making over this 16 millisecond time sample, if we fit the spectrum of the voice, where are the peaks and how big are they? So it does what's called an autoregressive fit. You notice that, you know that from signal processing? It does an autoregressive fit of the signal to find an all-pole approximation of the spectrum corresponding to the resonant frequencies of the throat and their amplitudes. And that's what it sends. This is suboptimal, but it's a lot easier. So when we let's see if this is actually turned on. So what we're listening to there now is you take every 16 milliseconds, you take 16 coefficients, you put them in RAM or in flash. On playback, for a 16 millisecond time interval, you take the 16 amplitudes that you have recorded, you synthesize a sine wave at the middle frequency of each of these bands, only a pure sine wave at the middle frequency of each of these bands. You multiply it by the amplitude and add them together, and that's what you play. So what's being played back is a very crude approximation of the input. The amazing thing is you can hear S sounds. There's no broadband noise in there. You're actually synthesizing back in the sounds of the S sounds, but your brain is synthesizing those in. So the reason I did this was twofold. One is it does an 8 to 1 compression and still makes understandable a slightly weird sounding voice. And secondly, it shows that you can do an awful lot of arithmetic on this architecture and still make a deadline on the interrupt service routine of 8 kilohertz or 16 kilohertz. Because now you're having to synthesize 16 or 30 DDS units running at the sample rate to reconstruct the speech. And it's possible to do the 30 channels at 16 kilohertz and still have time left over. So that was amusing. The amazing thing, though, is this is the average power spectrum of the input of those 10 digits. That's the average power spectrum of the output. They don't look anything alike, and yet you can kind of understand them. I don't pretend this is optimal. If somebody wants to get linear predictive coding, code-excited linear prediction, CLEP, going as a final project, that'd be interesting. I think it's doable. Doing the playback is certainly doable. Doing the encoding requires inverting an n-by-n matrix every 16 milliseconds, where n is the number of poles in a filter. I think it's doable. I think it's doable. I'm not sure. So that's the vocoder method. That's option one. One person held up their hand saying they're going to do it that way. And option two is, I'm going to tell you, I wrote a little utility early on. This was an early experiment that I was doing this. I wrote a little utility which takes a WAV file, truncates the samples to 4 bits, packs 2 4-bit samples into each car, into each byte, and then writes a C header file of those bytes. So the MATLAB program, which you don't need to run, builds the header file of the packed samples, which you don't need to modify. You do not need to modify. But these represent each entry. Those are a lot of zeros there is what those are. Each entry represents two time steps, 2 4-bit samples of the amplitude waveform. When we want to play this back, we're gonna traverse that. The amazing thing is here, that's the original power spectrum of the speech. This is called a spectrogram. Time in this direction, frequency in this direction. Power is encoded as a color, so red is higher amplitude than green. That's the original 16-bit sound. This is what it looks like after it's been compressed. Notice the band structure here is very similar to the band structure here, just a little bit washed out. So they sound a lot alike. And the playback program is really easy. So if we go down to the interrupt service routine, that's the entire interrupt service routine. Let me expand this slightly. Some timer 2 is ticking along at 8 kilohertz or so. And I'm using the VREF DAC. You do that. You have to put it out on a SPI channel, so that if you use this scheme, there'd be the SPI interaction code here. But basically, we're reading the header. We're reading the jth entry of the header, deciding whether it's an odd or even sample, and decoding either the top 4 bits or the bottom 4 bits, and then sending those bits to the DAC. If you're happy with 4 bits, that's all you have to do. This is what it sounds like.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
So it's a little scratchy, a little bit harsh, arguably more human sounding than the synthesis. And there's more bits there. It's only 2-to-1 compression rather than 8-to-1 compression. Either one of those is acceptable. You can use the WAV file system, but obviously modified not to use the VREF DAC, but to use the SPI DAC. Or you can do the spectral synthesis, or you can do any other method that you want, as long as I can understand the digits. There's one little twist that I haven't talked about, and that is that, I'll talk a little bit now and then more, and that is that virtually all of the code that I write for doing DSP uses fixed point arithmetic with a little library I wrote myself. It was probably not optimal, but it's faster than the floating point. The format, this is just a teaser for next time. The format that we're going to use is 1616 fixed point, so the 16-bit fraction, a 16-bit integer with the binary point halfway through the integer word. And so there's no difference in the way that bits are stored in memory, it's just how our brain interprets the bits. So if you take two fixed point numbers and add them using the hardware adder, is it correct? So if you take two 1616 fixed point and add them, do you get a 1616 fixed point?
Does it overflow?
As long as it doesn't overflow, you do. If it overflows, all bets are off. So add is free. Add is just exactly the same as an integer operation. Subtract is the same as an integer operation. The other operation, the other math operation we need for DSP is a multiply. And for a multiply, we have to do a small correction. Because when we do two 16 by 16 multiplies, or two 32 by 32 multiplies, the binary point now is at bit 31. And we need to get it back to bit 16. So the part of the number that we need is the 16 bits just above and below bit 31. Which means we need to shift the output. We need to shift the frame so you can see the shift. We need to shift the output by 16 bits. So the fixed point multiply is going to be the same as a long multiply shifted by 16 bits. And then there's various utilities. Float to fix, to take a floating number, turn it to a fixed point number, fix to float, fix to int16, int to fix 16, divide. It turns out that a fixed point divide is not faster than a floating point divide. And a fixed point square root is a good deal slower than a floating point square root. Why do you think that is? But, so what my fixed 16 does is float the number, take the square root floating, and then fix it again. That's faster than actually doing the fixed square root. Why is a float square root so fast? It's because half the work is done for you. It's already normalized to 1. The significand is already normalized to 1. To take the square root of the exponent, you just shift it 1 to the right. So half the work is done. We'll talk more about this next time. So I'll see some of you in lab.